In the next couple of videos, we'll look at random access memory, or RAM. One key characteristic of RAM is that it takes the same amount of time to transfer data, our binary data, into or out of any memory location in memory. So whether we want the first memory location, the 2016th memory location, whether it will take the same amount of time to write either of those locations and take the same amount of time to read either of those locations. We don't have to seek for the new location. So that's one key characteristic of RAM you should know. So if we talk about RAM, we typically talk about the number of bytes RAM has in general. A byte, as we recall, is 8 bits. A word, however, is really how we tend to read from RAMs in a system. So a word is the number of bits stored in one location, and it's typically a multiple of the number of bytes. So we could have 2 bytes, 4 bytes, 8 bytes, 16 bytes. A 2-bit byte word would be 16 bits. A 4-byte word would be 32 bits. An 8-byte word, 64 bits, etc. So the word size, that depends on the digital system. That's the number of bits per word. But we can go by the number of bits per word, but typically we'll be going by the number of bytes per word, since all words are in systems today are all multiples of bytes. So the capacity of memory, again, as we said, it typically states the number of bytes the memory can store. The address, that's how we get to the location in the RAM where the word is stored. So that's our unique identifier for each word is its address. So that will be the address to our RAM to seek the unique identifier for the word, and we access RAM one word at a time. So RAM is addressed by the word. Each word is assigned an identifier. That identifier is its address. If we have, for example, a 1 kilobyte memory, it has 8 kilobits because there's 8 bits per byte. So a 1 kilobyte memory has 8 kilobits. If the word is 16 bits, then we have 512 words in the memory in our 1 kilobyte memory, or 2 to the 9 words. So we need 9 address lines to uniquely identify those 2 to the 9 words. So we could work that out. Our 1 kilobyte memory, that's a 2 to the 10 bytes of memory, but we have 2 bytes per word, so we have 1 word for 2 bytes. So we have 2 to the 10 divided by 2 words, or 2 to the 9 words. So we could work that out. And again, so it's the number of words is what we have to address. The number of words is what we have to address. So we have 2 to the 9 different combinations. We can get 2 to the 9 different combinations in those 9 address lines. That's how we can uniquely identify each word in the memory. So if we want to create then a block diagram for this 1 kilobyte memory with a 16-bit word, well, let's look at what they show in the textbook. In general, we're going to need, for each bit in the word, we need n input data lines and n output data lines, right? So that n input data lines and output data lines, we need to address them by the multiple of 2, so we need k address lines, and then we need a read and write indicator. So the way we're going to create our block diagram, so we want all our variables internal to the block, so we can use them to build larger blocks. So you can do a /n to show the n inputs, input lines. DI I'm using here for input, DO for output. It's a data input, data output. And we'll go from n-1 to 0 to get the n lines. And same thing with the address lines, k address lines, k-1 to 0. So that's in general for a 2 to the k byte memory n-bit word. If we want to have a 1 kilobyte memory 16-bit word, then 1 kilobyte is equal to 2 to the 10 16-bit, right? So that's going to be our n. We are going to need 16 here, but that's equal to 2 bytes. So what we need to address is the number of of words. So we can divide that by 2 bytes per word. So that's equal to just 2 to the 9 words. So our K here then is going to be 9, and we'll go from our address here from 8 to 0, and this is going to go from 15 to 0, and again 15 to 0. If we had a 2 kilo word memory with 16-bit words, then we'd need 10 address lines, but we're looking at the kilobyte memory. So let's look at this example here, and let's just review. K is a kilo, that's 2 to the 10. M is a mega, that's 2 to the 20. G is a giga, that's 2 to the 30. So we want to remember our powers of 10. So this says if we have a 8 megabyte memory of 16-bit words. So our 16-bit words, that's 8 bytes, right? So 16 bits. That's we have 8 byte words, and our 8 megabyte memory, that's 8 is 2 to the 3, mega is 2 to the 20. So we have, 2 to the 23 byte memory, and we have 8 byte words. Well, that's equal to 8 byte words, or 2 to the power of 3 byte words. So that's how we have to determine the number of address line we need. The data input lines, we need enough data input lines for each bit, right? So for each bit we need 16 data input lines. We're going to need 16 data output lines. How many words are we able to store in memory? We're able to store we have a 2 to the 23 byte memory, and we get 8 bytes. We get 8 bytes per word. So we have, I can't fit it there, so we'll do 2 to the 23 divided by 2 to the 3, and this is bytes, and this is bytes per word, right? So that is equal to 2 to the 20 words. So we have 2 to the 20 words stored in memory. So we'll write that here. That's 2 to the 20. So we need 20 address lines, right? So that's our K. We need the 20 address lines. So that's how we want to convert it all to, it's easiest to convert it to powers of 2, right? If we convert to powers of 2, we can easily divide, and then while you're trying to make sense of it, just use your ratios of units, and so bytes per word, we have 2 to 3 bytes per word, that's equal to 1, so we can divide by 1. All right, so if we look at just the content as an example, if we're looking at contents of memory, I said we can think of it as an array. So if we have this 1 kilobyte memory, we have addresses between 0 and 1023. Each of these are the contents of memory. So if we look at inserted at address 0, we have this array of 16 bits, right? Because they're 16-bit words. If we look at address 1023, what's stored there, what's going to go in for our memory address will be all ones. The decimal equivalent of that is 1023, and this is what we would read from memory if we were reading memory, if this was what already was stored there. So again, our memory address lines are in binary. We can represent that number in decimal to make it easier to read, and typically what we can do in here with our memory contents is also represent that in hexadecimal, if you recall. That's easier to read. So in general, we have n bits per word, we need n data lines going in and data lines going out. We have m number of words, and k address lines, so that 2 to the power k, that's got to be greater than or equal to m. Typically that's equal to m. And again, if we were to, as an example here, if we wanted to represent the content of memory address 1023 down here, it's difficult to read, but we could represent that more easily in hex, just like it's easier to look at talk about the binary address as its decimal address. We could also talk about that as its hexadecimal address, but represent that in hex. We have a 5, a 2, and that's an E, and that's a D, right? Yeah, DE25. So that's the way, if we had a computer program, we could spit that out instead of having to read all the ones and zeros. You can state that as sort of a higher level of abstraction, so that it's easier for the human user to be able to interpret what's going on in binary. All right, so that's our introduction to RAMs. We'll talk in the next video about read and write operations.